So I'll go through some problems to illustrate each of these applications. First one, Starbucks wants to know if preference for coffee blends is equal across three options: light, medium, and full-bodied roasts. And of course, this would be important to them for product development and for inventory management. So they survey 100 people, and they get the following results. 20 people preferred the light roast, 45 preferred the medium roast, and 35 preferred the full-bodied roast. So the question is, are these results statistically significant at alpha equals 0.05, which means they want to be 95% confident in their conclusion about whether this sample represents a population in which people's preferences are equal. So that research question is set up as a statistical test, such that the question is, are the frequencies of preference different from expected? In this case, expected equals the same. Thus, the null hypothesis is that we should observe 33.3% of the responses in each category. And the alternative hypothesis is we would observe something other than 33.3%. And any deviation, or deviation in any direction that would constitute support for H1. So the appropriate test here is chi-square. We have three groups, which automatically eliminates t-test. Remember that t-test can be done only for differences between two groups. So the data look like this, and this is the way one would do the calculation by hand, and this represents how the computer would be doing it. You see the light, medium, and full-bodied are our three categories. The observed frequency is the number of people in each frequency, 20, 45, and 35. The expected frequency from our null hypothesis is that we would see 33.3, 33.3, and 33.3. The next column is the observed frequency minus the expected frequency. So it's 20 minus 33.3, 45 minus 33.3, and 35 minus 33.3, yielding 13.3, 11.7, 1.7. And notice I'm ignoring the signs here, so it doesn't make a difference whether it's 13.3 or minus 13.3, because in the next column we're squaring that number. So we're going to have positive numbers anyway. So this is the observed minus the expected frequency squared. So 176.9, 136.9, and 2.9. And then the final column is the contribution to chi-squared from each cell, which is the observed minus the expected, the quantity squared, divided by the expected. So that's 176.9 divided by that expected value of 33.3, yielding a contribution of 5.3. And 136.9 divided by 33.3, yielding a contribution of 4.1. And 2.9 divided by 33.3, yielding a contribution of 0.1. Remember, chi-squared is the sum of those, so we add them up, and we get a chi-square observed of 9.5. So we can see that this distribution deviates from the expected, and a measure of the extent of that deviation is the chi-square observed at 9.5. So is that enough deviation for us to be 95% confident that the sample does not come from a population with equal proportions? Yes, because the chi-squared critical value with 2 degrees of freedom, remember k minus 1, we've got three categories, is 5.99 for alpha 0.05. So since 9.5, the observed value, is greater than 5.99, the critical value, we would conclude that yes, there is a difference in the proportion that exceeds what we would tolerate as error from a population where the proportions are equal. And that is our final step in this analysis. We interpret the test. Yes, the frequencies of preference differ from expected, and the conclusions we draw are to interpret those differences. So we don't simply say, hey, the scores across this question were different enough to conclude they're not the same. We look at what those scores are, and so we would say people differ in their preferences. Most prefer medium blend, and fewest prefer a light blend. So we go back to the table and see that the largest contribution to chi-square came from the preference for medium blend. A second problem. The MBA program committee wants to know the average GMAT score for prospective applicants. So they sample 100 people. The average is 520 with a standard deviation of 44. The committee wants to know how precise this estimate is with a certainty of 90%. That is, alpha equals 0.10. So the question is, how close is the average population GMAT score to the sample score of 520 given a certainty of 90%? And that's essentially asking what the confidence interval is around the mean of 520. Well, that's a problem that should be easy enough for us to solve. We have the equation for a confidence interval about a mean. It is x bar, the sample mean, plus or minus the t critical value times the standard error of the mean, which is s over the square root of n. We know that the t critical value for an alpha of 0.10 is 1.65. So our confidence interval, simply by substituting these values in, is the sample value 520 plus or minus 1.65 times 44 over 10. That is 44 the sample's standard deviation and 10 the square root of n, which is 520 plus or minus 7.26. So from this we can conclude that with 90% certainty the population mean lies within the range of 520 plus or minus 7.26. Problem 3. A firm wants to know if recent marketing efforts have improved satisfaction above last year's estimate of 88% satisfied customers. The same survey is done. This one indicates 91% were satisfied. Is this a statistically significant difference at alpha equals 0.05? So in other words, the question is, has satisfaction truly increased, or is this improvement merely a random fluctuation that we would expect in the population? So the test is, well, satisfaction appears to be measured on a yes-no scale. So we're looking at the test, a test of difference in proportions. There are 3 ways we could test this. We could do a t-test of proportions, asking is 0.91 greater than 0.88, or we could construct the confidence interval about the proportion 0.91 and see whether 0.88 falls within that confidence interval at 95% certainty. Or we could do a chi-squared test looking at the distribution of 0.91 and 0.09 and asking whether that's different from the expected distribution of 0.88 and 0.12.